things not rotate. So make sure you know the difference between previous topic where you deal with moving things and this topic where most of the time you tend to deal with things that stay at rest. Now, those of you who have read a lot about physics would have read about the 4 fundamental forces of nature. I'm trying not to move too much because I realize the microphone connection is temperamental. But just like all teenagers, you just have to get over it. So now, those of you who have read, right, the 4 fundamental forces of nature, right, these are the non-contact forces. And you will have read about why they are important. For many of you, right, only the 2 forces on the left side, meaning the gravitational force and the electromagnetic force, relevant to your everyday lives, you can see it. The nuclear forces, unfortunately, you cannot see and experience that because they happen at a scale way too small for you to directly experience them. But the thing we want to do are contact forces. That means the objects need to touch one another before the forces are transmitted. And we will start by tension. Now, I'm going to differ from the other lectures. I only have one face-to-face lesson with you, so I will go through the main physics ideas here. Nearly all the examples and the videos that supplement the learning will appear on SLS. So I will touch on all the important ideas you need to have. So please bear with me. I'm going fast and furious because I would like to cover the 3 main ideas. So first will be on tension. Now the basic idea is this. Tension is a bidirectional force. Meaning bidirectional. Now, if I let go, it goes this way. If I let go the other side, it goes the other way. It seems to show that tension, right, has 2 directions, and this is what we need to know. It's a bidirectional force. And if you were to analyze whatever is written there, you will see that if I set up this system and the whole thing is in equilibrium, meaning nothing moves, then all the forces there must be equal. How do I know this? You can, of course, look at object 1 alone. If you look at object 1 alone, object 1 does not move, so force F1 must balance tension at that point in time. Notice the tension in the object is also pulling on object 1. Now if you analyze object 2 on itself, right, F2 must balance the tension T2. And since I said that the whole system is equilibrium, these 2 forces that pull them must also balance, because if the forces not balance, then this whole system must move either to the left or to the right. So once you do this, you realize all the forces balance out. And the important thing to take note, right, the direction of tension will always be opposite to the force responsible for creating the tension. So the one important thing is actually found in the last statement. And you do this sort of question very often in chapter 3, under dynamics. You have that thing, and you are always told, right, these 2, right, when they are connected by a string, the tension, and all of you will draw, oh, tension here must point up, and then this must point this way. I'm not sure you can see this clearly. So you will actually see this, and then the students will always wonder why. If you analyze carefully, the individual objects, this is how you will draw the free body diagram for object A and B. Easiest, of course, if you look at object A. Once you know object A is being pulled down by gravity, then tension in the string that holds it up must point up. Then once you know tension is bidirectional force, if tension in the string here or object B is pointing up, then this tension in the string must point the other way, because remember, tension is bidirectional. So that is the easiest to learn. It took me a while to understand the concept of tension. And later on, you realize that tension, a lot of times you study, right, apply to massless object, the tension will be the same value throughout. So that's why when you do this sort of question, they always tell you the string is very light, so you need not consider its mass. The reason why that is so that there's only one value of tension throughout the string. But that is story for another day. Unfortunately, I have to go on. The same will also happen for compression. So if you try to compress the spring, unfortunately the spring doesn't allow me to compress, but you realize in order for you to compress, right, I need two forces in opposite direction to compress. So what happens, right, when you apply these two forces for F2, F1, right, the object, right, will provide two forces that point out. And again, right, the key thing, right, you will notice that the directions of the compression acting on the object side will always be opposite to the forces that is responsible for creating the compression. So I assume I've written enough there for you to read. So let's talk about Hooke's law. Whenever you deal with springs, you will deal with Hooke's law. Yeah, we're now moving merrily along to page 4. Now suppose I have a setup, right, whereby I apply a force so that I stretch the spring from the initial length, which I call L naught, or what you call L0, that's L naught, and I stretch it to L, you realize the force has created an extension. The extension is called X, which is just the difference in the length. And Robert Hooke, who discovered this, right, he named this after himself. I said that, oh yeah, the force you apply, right, must be proportional to the extension. Those of you who have actually played with springs, you realize if I hang a weight here, this will pull so much. If I hang heavier, it will go longer. I hang heavier still, then you realize that force you need to stretch this, right, must increase with the extension. I'm not sure whether that's practical on this slide. In terms of equation, it is written this way. Those of you, right, wherever you have a proportional relationship, F proportional to X. This is a proportional relationship. To change it to an equation, I have to introduce a constant. So the constant in this case, right, they call it the force constant. So when I want to change F proportional to X into equation, I just introduce a constant K, then it becomes F equals to Kx. Now the K, right, sometimes it's also called the spring constant. How I wish I was in a country where spring is always constant. Now this is the graph. Now this is a graph that you will plot when you have a spring system. Now Hooke's law will apply for a certain length. So section OP, right, where you get the straight line that passes through the origin, is Hooke's law. Hello. All you should know that a proportional relationship, right, you will always get a straight line graph passing through origin when you plot it on the graph. That is the simplest way to visualize what is proportion. And so, of course, those of you, right, who are more mathematically inclined will also realize proportion means this. When X doubles, F doubles. When X increases 10 times, F increases 10 times. That's the basic idea of how proportional works. Now, after that, right, you were to plot or get data to plot the graph, right, it will no longer become straight. So point P will therefore be called the limit of proportionality. So if you want to find the spring constant, you will therefore use the gradient of the straight line part. And based on this graph, right, you can of course take just F prime over X prime. So based on this graph, right, you realize that, oh yeah, gradient is just F prime over X prime. But those of you who would like to read other coordinates and find the gradient, yes, you can also of course do so. Yes. Now, connecting springs in series and parallel, such questions are quite rare nowadays. It used to be more common, but we have to talk about this. Springs can be connected in series and parallel, just like resistors. And now, whatever you learn for resistors, right, what you do, you just reverse the idea. When I connect the springs in series, the spring constant becomes smaller. So this is different from resistor where you connect resistance in series, right? The resistance becomes larger. But here, right, where I connect them, right, the spring constant becomes smaller because if you think about this, right, this is the same force. Okay, so this force, right, which I pull, this force is applied to this spring 2 and spring 1. So can you see that it's the same force throughout? This force, right, when you apply to both springs, right, will produce an extension. So the overall spring system becomes longer because each spring extends due to this force. Then end up the extension, then realize, oh, easier to stretch. Remember, spring constant measures the stiffness of the spring. So when spring constant is very high, means you need a lot of force to stretch it. So if you look at when I connect them in series, you realize I can create a longer extension because each spring extends by a little bit, so I add up, total extension is larger. Now what happens when you connect them in parallel? You will realize that if I connect in parallel, right, this F, right, seems to split into F1 and F2, such that F1 plus F2 must equal to F. You see that the force acting on each spring now becomes smaller, so the extension created will be smaller. So it seems like it's harder to stretch two springs in parallel. Therefore, the spring constant, realize you add up. But you're not required to derive this, it's just for you to know, so that next time when you have spring systems you need to set up in the future, you will know how to set them up so that you can make them stiffer to stretch or easier to stretch. Are we okay? Now that's one contact force. Now we'll move on to the next contact force, normal contact force. Now this is called normal, not because it is not abnormal, but because we use the mathematical meaning of normal, meaning it's perpendicular. So this will always deal with, when surfaces are in contact, you deal with the perpendicular force, hence we call it the normal contact force. And if you were to color code this, I color coded so that it's clear that the yellow force and the green force, right, they do not act on the same object. And this was covered in Mr. Ho's lecture. Because you realize they form an action-reaction pair. The weight of the object acts on the object. So the contact forces, right, they are action-reaction pair because you realize one is contact force by object on surface. The other one is contact force by surface on object. So those of you who have studied Newton's third law well, right, I normally tell students, Newton's third law actually, if I were to think about it, is that forces always come in pairs. That's the genius of Isaac Newton. It comes in pairs in such a way such that when object 1 acts on object 2, right, it applies this force. The same magnitude of force, right, will be applied back by object 2 on object 1. Now, W and the normal contact force, right, acting object, they are not action-reaction pair because they act on the same object. But this is covered in the previous topic, so let's move on and talk more about contact forces. Now, this is where the scientists who did this, they are not consistent. Yes, we can call it normal contact force. Those of you who have read a lot of physics texts, you realize that sometimes they call it normal force. Sometimes they call it normal reaction force. But whether it's normal force or normal reaction force, they all refer to this normal contact force. When something is touching something, that is a contact force. Now, other examples of normal contact force applies when you have curved surfaces. When the surface is flat, it's actually very easy. Now, for example, in this flat surface, right, it's very easy for you to decide, oh, this is perpendicular, and therefore that's how the normal forces act. The difficulty comes when you have curved surfaces. So for curved surfaces, right, the last one, notice, there is this point in which they are in contact. Therefore, how do you do this? Like how you find gradient of a tangent, what you do, you have to draw a tangent line. So you need to, at this surface, this point, right, you draw the tangent line. Then after that, oh, once I draw the tangent line, I can draw the normal contact forces. Now in my notes, I also further added, right, not only are they perpendicular to the tangential line, this force, right, actually points to the center of curvature. So if this is a circle, right, and you have the center of the circle, this force actually will point to the center of the circle. And you can color code this so that you realize they act on different objects. This color coding is necessary at the start where you need to see that the two contact forces, they really act on different objects. And now things become more interesting. Friction. Friction acts parallel on the surfaces in contact. So remember, you have normal contact force which is perpendicular to the surface in contact. Now I have friction, and strangely, friction acts parallel. So I have normal forces, I also have parallel forces. And we look at how you walk. It would be nice if I could have you demonstrate how you walk. But imagine you're trying to walk. What do you actually do when you try to walk? You are actually trying to use your feet to push the ground back. So think about when you walk, right? You are actually trying to push the ground back using your feet. And if there is friction by the ground, right, the ground pushes you back using that same friction. So therefore, you move forward because of friction. This should have been covered in Sec 3. And all of you know this because when you are young, when you start learning to walk, it took you some time because it took you some time before, oh yeah, you understand the physics of how you walk. So that's why babies, right, will take like at least 10 or 11 months before they grapple, oh, this is how I walk, I must always push the ground back. So it's not easy. Now think about this. If there's no friction, you will realize there's only one. You are trying to apply the force, so what will happen? You will probably visualize this as there is no grip. Then what happens? This foot will just, and therefore you fall. Make sense? Take note, if there is no what you call grip, or this surface is very smooth, where the friction is very small, what will happen when you try to push the ground back is your foot will just go this way, move to the right. I wonder why, maybe that's why they call it slippers. But never mind, let's talk about friction. Now, when you deal with things that slide on surfaces, right, it's actually quite easy. The difficult part is when it comes to rolling. I will admit, even up to now, right, I sometimes have difficulty identifying friction for rolling. But the basic idea is this. If I have this setup, I want the wheel to turn.
Now, as mentioned, frictional forces involved in rolling motion can be a bit more tricky to handle. Now, let's consider this case where you have a wheel that is not moving, it's not rolling. So it is a stationary wheel. And what we're going to do, we're going to push this wheel from the right. Now we apply a force at the center of the wheel because we want it to move. Now the instant we do this, you will realize that at the ground provides a frictional force at the bottom of the wheel, because if you imagine this wheel, right, as a square box, so if you were to push a square box, you will realize what happens. The surface in contact, the surfaces, you will see that the box wants to move to the right. So same thing here. When this wheel, right, when you push it this way, this wheel, right, wants to move to the right. So we can see that at the point of contact, the motion is to the right. Now, since friction is a force that opposes this motion, it will point to the left. So that's why friction points this way. And you realize there is a frictional force applied from the center of the wheel, and this causes the wheel to rotate. So this is interesting because it is friction that makes the wheel rotate. So take some time to ponder about this so that you get a clear idea why this happens. As I've said, the key thing to take note is, number one, I'm going to push the wheel to the right. So I apply a force to the center of the wheel. So at the point of contact, which is at the bottom, you can see that the wheel wants to move to the right because of the pushing force. Now friction, right, will therefore oppose this movement, and therefore friction will point to the left. So there is a frictional force that points to the left, and this will make the wheel rotate clockwise, because once you have this frictional force applied here, you see that this will set up a turning moment that will make it rotate clockwise. Now next, we're going to look at other cases for rolling. Imagine a wheel that's being turned by an external force. You can imagine that the wheel, right, that is connected to an engine, or you are pedaling a bicycle tire. So imagine you are the one responsible for providing a force to turn the wheel. So in this case, right, the wheel is turning. It's turning because there is something that provides a turning moment for it to turn. So in this case, right, this external force, right, is making the wheel rotate clockwise. So you can see that the wheel is rotating clockwise. Now look carefully at the point of contact at the bottom. If you look at the point of contact at the bottom, you'll realize the movement of this surface, right, is to the left. So this movement of the surface is to the left. So the frictional force, right, to oppose this motion will point to the right. Therefore, you notice that this frictional force points to the right, because at the point of contact, the wheel surface, right, is actually moving to the left. So it's this frictional force that actually makes the wheel move forward. Now this will be clearer in the next example. Now this applies to those of you who have sat for the O levels. Now we have done the O-level syllabus, you will have seen this question in your 10-year series. And if you read the question carefully, the wheel here is connected to the car engine. So it's connected to the engine. So the engine is making the wheel turn. In order for the car to travel to the left, you realize the wheel must be turning anti-clockwise. And once you know this, right, you will see that at the point of contact at the bottom, right, the wheel surface, right, is actually moving to the right. Friction opposes this motion, so the frictional force on the tire will point to the left. So the correct answer is actually D. For those of you who have done O-level, you should know this answer. Now, you can actually take a step backwards and then think about this. In this whole question, right, let me erase all the forces. Sorry. Let's erase all the forces. And then you look. The car is accelerating. So actually, the tire must also be accelerating to the left. So take note. In this question, right, it says the car is accelerating. Now, the direction of travel is to the left. So the tire must accelerate to the left. When you ask, what is the force that make it accelerate to the left? So if you look at this, right, there are no other forces that act on the wheel. The car engine actually turns the wheel round and round. So what is the force that makes the car go to the accelerate to the left? It must be frictional force that points to the left. So therefore, if you analyze it this way, you realize the answer also happens to be D. So that's why when we deal with rolling motion, sometimes it's not as straightforward, but the most important idea that you must have is friction, right? It's always a force that opposes the direction of intended motion. So always analyze at the point of contact how the surfaces are moving. Once you know that the surface is moving one way, then friction, right, will always point the opposite way to oppose that intended motion. So once you are clear about this, it will become a lot easier to manage rolling motion.
We're dealing with not so difficult question here. Drag forces, you know drag forces because all of you have run through air or you have swam in the water. You have encountered air and water resistance. And for low speeds, right, the drag force or the resistance force, right, is proportional to speed. For high speed, right, it's proportional to velocity squared. But whether it is proportional to V or V squared, right, the key thing is drag forces, right, they increase with increasing speed. The faster you move, the larger is the resistance you encounter. Those of you who are swimmers will know this. The faster you swim, the greater is the water resistance. Those of you who are champion runners, the faster you run, the greater is the air resistance against you. The basic idea is it will always increase with increasing speed. And now I want to talk about this thing called reaction force. There is a reaction force. And I already mentioned, you will always have a reaction force when objects come into contact. So now I'm going to consider a ladder. I think I've used the same ladder there. Now, when I lean a ladder against a smooth wall, take note, there are 2 points of contact. One on the wall, so can you see that there are 2 points of contact. There's contact point here, and there's contact point there. So these 2 points of contact will give you a reaction force. So there are two contact points, therefore two reaction force. Because remember, every time I touch something, I apply a force on something, that something gives a reaction force back. So that's why when you slap people, right, the people experience your slap, your hand also experiences the force exerted by the face back on you. So that, notice, your hand slows down after it comes in contact because there's a force to slow down your hand. Now, let's analyze R1. Because R1 looks easy, looks like the normal contact force. Because R1 is really just a normal contact force, because there's no friction. It's a smooth wall. So, the reaction for R1 is the normal contact force. So R1 is easy to understand, because, oh yeah, it's in contact with a surface, normal contact force. But it's because of that, because this is a smooth wall. If you look at the ground, right, if you analyze the reaction force, it points at a funny angle. So those of you who know, this is not just the normal contact force alone. So let's analyze this in greater detail. So when you have this setup, friction must play a part. Why is that force necessary? Is to stop the ladder from sliding. So take note, the frictional force points to the right, because if there's no friction force, what happens to the ladder? It will slide to the left. I'll try doing this, see whether it works. Now, take this against mine. So notice, if I put it here, right, this thing leans quite nicely. So if I try to do it here, right, where it's smoother, right, this slides down. You see, this is a rough surface, so the friction it can give you is a lot higher. So this thing stays in place. But if I try putting here, right, it slides that way. So notice that in this demonstration, right, there is friction involved. Wherever you lean something on the floor, there, if this thing is successfully leaning, there must be friction. So if there's friction and there's normal contact force, you know that there are now two forces. The reaction force is just the vector sum of the two forces. When I mean vector sum, right, you learn this in topic 1. The reaction force is, you have Pythagoras theorem applied, and then you have this tangent theta applied. So you've done this in topic 1. And all of you amazed, oh, how everything from topic 1 up to now, all linked. Now please do not confuse this reaction force. If they call it reaction force, right, please do not confuse this with the normal reaction force. Remember, sometimes people call the normal contact force as normal reaction force. Because whenever you touch a surface, there is a reaction force. So just remember that if the question talks about reaction forces, right, don't assume it means normal reaction force. If it's normal reaction force, they'll say normal reaction force, which you then, in your mind, oh, normal contact force. And now you can do turning moments. Now you've done this in your secondary school days, but most of the time in your secondary school days, right, your forces and your distance, right, they are usually perpendicular, so it's quite easy to see perpendicular distance. The thing is, now we have to introduce how you solve it when the distance from the pivot and the force, they are not perpendicular. So many of you have drawn the line of action. I believe your Sec 3 teacher told you, draw the line of action. That means you extend the force line. So this is the line of action, because this is the direction in which the force acts through. So you extend this line, and your teacher will probably tell you, this is a line. This is your pivot. This therefore is the shortest distance. That is the correct perpendicular distance to take moment about. So in terms of math, right, you realize if I define R and F, and there's an angle phi, then this will be FR sine phi. So now we have to link all the way back to what you learned in Sec 3. And now we have to talk about couple. No, the couple is not what you think of. Even though you're the right age to start thinking about couples. Now the couple, right, in physics terms, right, means this, the pair of forces. And there are quite a few conditions. They must be equal in size, but they are in opposite directions. Their lines of actions, right, do not meet at the same point. And a couple, right, in this case, right, it will not move the object. It only serves to rotate the object. So this is a simple idea of a couple. But as long as you all have two forces, right, it need not be a circle. You just have any object. If I apply a force this way, a force that way, right, I will have a couple too. And they will introduce this thing called torque of a couple, which is defined as the product of one of the force. Take note, you take one of the force multiplied by the perpendicular distance between the two forces. So that's how you find torque of a couple. So what is a torque? Just like a force produces acceleration, a torque produces turning moment. So torque basically is the equivalent to force. Force makes things move in straight lines, whether accelerate or decelerates along straight line. A torque produces rotational motion. So those of you who are into sports car will realize they always talk about torque, maximum torque of the car engine, because the car engine is used to turn something. Therefore, torque becomes turning moment. Principle of moments. So when you win awards, right, you realize Madam Choi will always have that point in time to come and talk to you. That is principle of moment, because there's a principle having a moment. Oh, let's celebrate your achievement. Never mind, I'll assume you're temperamental. Now, principle of moments, right, is correct for any axis. Now, in your secondary school, you learn it about a point. Now, we want to extend to an axis. Remember, axis is just a line that passes through a point. And those of you in Sec 3, right, you will have played around with, I can take moments about any point I want. It is balanced. The clockwise moment and the anti-clockwise moment are always balanced. And this does not depend on which point I decide to take moments about. I can choose any point in my pivot if something is balanced. If I choose something and balance it, I can take moments about anywhere. I can take moments here, and I look at the forces. I'll find that the forces, right, will produce clockwise moment equals to anti-clockwise moment. I can take moments about here. I can take any point I want. As long as balanced, this principle was applied. Now you can refer to example 7 and 8, which serves to highlight this point. Those of you, 7 and 8 allows you to solve it using alternative methods. You can take different points to take moments. You realize answer will always be the same. But the trick is usually you take moments so that the working is simpler. And now static equilibrium, finally. Remember, I did say that we want to study this topic which analyzes forces in static equilibrium. So what is static equilibrium? Net force must be equal to 0. That means if the sigma sign there means the summation of all forces must be equal to 0. Why is this necessary? Because when the net force equals 0, the thing will not move. I need the resultant torque about any axis to be 0. For those of you, I've used the symbol tau to represent torque. This is quite a fairly universal symbol for torque. They use tau. Why must the sum of moments be equal to 0 or the sum of all torques? Remember, a torque is required to produce turning moment. So all the torques, right, must add up to give you 0 turning moment so that the thing does not rotate. So now we come to the idea. What is static equilibrium? When the object does not move, when it does not rotate. That's it. Simple, right? Now let's talk about equilibrium under three forces. Three is a very nice number for force because then you can analyze it quite easily. Now, if there are three forces, right, and you know that the object is in equilibrium, you can then draw closed vector triangle. Now, this is found in example 9 of your notes. But I think I briefly just drew this. Now, in your notes, you will have this diagram where this is an object. The green object has three forces acting on it. Now, if it's in equilibrium, right, I can then make it into a closed vector triangle. What is the meaning of closed vector triangle? You start anywhere. Suppose I start here, so I take this point. I follow the direction of vector. It goes down, goes up, goes up. We will go back to the same point. That means this triangle is closed because the direction shows a closed loop. So this is an anti-clockwise loop. I can also do a clockwise loop. When I do a clockwise loop, I can start here, then I will come back to the same point. So this is called closed vector triangle. This shows that this is in equilibrium. If I'm not wrong, most of your secondary school teachers will talk about this. Now, just to let's see, I want to end the slideshow. This for those of you who know, right, what I've done, right, you can actually see that this is they are actually the same. So what I did is, this here, then this goes down. Oh, now this can pick it up. Sorry, my IT skill not advanced enough for me to animate. I tried animating this, but it always ends up being an open triangle, but not closed. So my fault. Now let's continue. What happens when you have 4 or more forces? Then you will have closed polygon. So if you, in the example in your notes, right, because it's 5, actually, if you bother to draw this out, you can actually make a closed polygon. Other special cases. Now we want to talk about special cases for things that are in equilibrium. Now for this, for simplification, right, I will only consider coplanar forces. That means forces that act within the same plane. Because your maturity level not allow you to do 3-dimensional yet. So if you do 3-dimensional, then you realize, oh, it's a lot more fun. But for now, we will do the fundamentals so that all of you are very good in doing 2-dimensional setup. So what happens when there are two forces? To achieve equilibrium, the two forces must be like this. They must have the 3 conditions applied so that I can have equilibrium. So all 3 conditions are necessary. So now I'm going to prove to you. Suppose I don't have number 1, they are not the same magnitude. Then you realize upward force is larger than downward force. For sure, this object will accelerate upwards. Correct? So that is first condition, so it must be obeyed. Now, suppose if I ignore the second condition, they do not have the same line action. That means I cannot draw one line that passes through both forces. Then you realize this forms a couple. This object will rotate, will not be in equilibrium. And what happens if they are not opposite in direction? Now I have two forces that meet at the same point, but they are not opposite in direction. You realize there is a resultant force pointing somewhere diagonally to the top right corner of the stage, not the stage, the wall facing the stage, right? You realize this will also accelerate. So all three conditions are necessary. Wow, what about three forces? If I want to achieve equilibrium with three forces, right, they must either be all parallel. Like in this case, I can use two strings, right, to hang this, and you realize it will be like three forces, tension T1, T2, and the weight. And I can make this be in equilibrium. So three forces, but all the forces are parallel, so it seems to work. Now comes the interesting one, or they must be concurrent, meaning they all meet at the same point. And again, I'm going to use the ladder. You realize when I drew this diagram, right, R2, R1, and W, right, if you extend the lines, they will all meet at one point. They all intersect one point. So this is called concurrent. And if this is achieved, right, then for sure this ladder is the equilibrium. So take note, even though I use a ladder here, it can apply to anything but in which you're in contact with. Now the concurrency condition, right, meaning the forces are concurrent, unfortunately fails after four forces or more. It works for three, but four, right, sometimes it works, but often it does not. But the concurrency condition, right, is can be applied. So you can see example 10. Now in SLS, I'll work through all the examples to flesh out what I'm talking about here. So example 10 is the one that you can use the forces must be concurrent to find the direction of the third force. But sometimes, just because forces are concurrent, right, may not allow you to solve the problem completely. So this is example 11. So example 11 is interesting, so I'll spend a bit of time here. I'll probably the last thing that I do. So this is example 11. On page 20 at this. So there are options A, B, C, D, E. Which one shows the ladder in equilibrium? Take note, it says that the ladder is about to slip or about to slide. That means it's still not sliding yet, so it's still in equilibrium. So here there are 5 options. I will tell you, I will use the concurrent condition to find the answer. So straight away, right, you realize option A, D and E cannot be the correct answer because they are not all parallel, but all of them, if you look at A, D and E, right, the forces do not meet at one point. So straight away, you ignore A, D and E. Oh, you only look at B and C only. This is good, right? Because straight away, 60% of the question is done. Okay, I only have this 40% left to decide which one. So let's look at this carefully. If I look at B and C, right, here comes the problem. If I were to draw the lines, you realize that this goes here, this goes there. Actually, it meets at one point. Sorry, I can't. B and C satisfy the concurrent condition. Because if you extend the line, they will all meet at one point. So then how do I solve the problem? So how do I solve the problem? I will have to analyze reaction force X carefully. Because you realize the difference between the two diagrams is only reaction force X. And then what you do, read the question carefully. Notice I've highlighted two words. It's leaning against a rough wall. When you see the word rough, straight away, a bell must ring or light bulb must light up and think there must be friction. So the reaction force X, right, has friction component. Then you read the question, it says this thing is about to slide, therefore it must look like this. Because the ladder, it were to slide, can you notice the bottom of the ladder must slide to the left? That means that this ladder, right, actually will go down this way. So it will go this way. So notice the ladder must come down and then it must move to the left. So I want to stop this from sliding down. You realize the rough wall must provide an upward frictional force. So this friction force points up, therefore the reaction force, voila, points diagonally up, and therefore you realize C must be the correct answer. Okay, so with that I've settled this. I know time is up. Although I just have 2 slides, but never mind, I will put that on SLS. There's now only upthrust and the principle of flotation left. So I hope you got the main idea about how to deal with forces that result in static equilibrium. So, thank you everyone.